let's see. Um, so today, what we are going to do is we're going to um, sort of wrap up the kind of conservation laws and Lagrangians and the action that we have been doing, so that from the next day we can start on our special theory of relativity. Okay, and so that's the plan. Now, things that I'm going to do today will have a little. Sometimes it will be uh, slightly more algebra oriented. So what I suggest is that uh, write down as I sort of try to walk through it. Write it down carefully, look at it, and try to go through this between today and the next day. Try to understand what went on in this algebra, okay, how we got the results. Because I won't have time to do all the steps, which is basically your homework. Okay, so the last thing that we did was basically we did a new kind of conservation, which is not there in mechanical systems. So it's not a conservation of energy or conservation of momentum or angular momentum, but it's particular to ED, which was the charge conservation. So we calculated what led that to work out some more conservation examples in ED. Okay, so if you think about uh, this local conservation law of electric charge, so this electric charge, of course, is a property which is basically carried by the particles, not by the field, right? Now, in contrast, properties like this energy, linear momentum, angular momentum, these are mechanical properties, and this is contribution both from this particles as well as these fields. Okay, so these lead to conservation laws, which are what are like conservation of the total quantities. So it's like a total conservation law. The total energy is conserved, total angular momentum and linear momentum is conserved. But for the electric charge, for conservation, we saw that the local conservation law was there. So the question is, can we have other local conservation laws? Instead of total conservation laws, can we have other local conservation laws? Okay. So to give an example, if you have the time displacement, time translation, then it basically of the whole physical system, then it gave you the total conservation of the total energy. Now, if I go and look at a small part of the system, okay, there's a very small part of the system, and over there you do a small time translation, then question is, would you get some conservation law which will be very local about it? Okay, so idea is, can we have time displacement of this part of the system which will have some energy information about that part of the system, not the whole system? Okay, and this is where we are going to see whether we can have local conservation laws, and so for small time displacements. And obviously, when I think of small time displacement, the way to think of it is, of course, of a very small, infinitesimal small time displacement, okay, which of course depends not only at the time when this time displacement happened, but also the position. So our time, infinitesimal time displacement is a function of both position and time. So let me try to write down what I meant over here. I think immediately, can I say, yeah, it has lost. So I have to again share the screen. The sharing screen goes away if you do not write anything, even for like 5 minutes. It's stupid. So let's start. So what did I say? I want infinitesimal time displacement. Okay. So let's see if we can have. So can we connect local, let's say, time displacement to local conservation laws. So let's have an infinitesimal time displacement. Okay. So what you want is you have a mechanical system. I want what is the response of the mechanical system to a very small infinitesimal time displacement. So we want response of a mechanical system to an infinitesimal some scalar, some lambda. Okay. And scalar is basically very similar to the scalar that goes in the gauge invariance. So lambda is a function of R and T. And I want to find the response of it to delta. The way we think of response is we can think time is displaced at some position. Time is displaced by from t plus delta t. The lambda, of course, has a new value, which is lambda plus delta lambda r. But since these two are very close to each other, they are almost the same. Okay. So this is what we're going to use. So what we do is that lambda plus delta lambda at, let's say, r and t plus delta t. Okay, this is a first simple assumption. Okay, so these are very close to each other, so these are very same. Now given this, what we can find, we can expand this, so multiply, make it into products terms and expand it in Taylor series. And so from here, what we can find is we can find what is my, so this gives me, so do this calculation, gives me R T del T. Now remember that these gauge transformations, we have transformations, so we have these gauge transformations, which was in one case, it was my A going to A plus with lambda, and in other case, my phi was going to phi minus 1 by C del lambda del T. Of course, these are all function of R and T. So what I want to actually see is when I have this small change in the time, the response of something, the small change, local change the time, how does that response affect these quantities. By C del 2 lambda del T2, okay, because we have to take the derivative with the Stratus function, and then minus 1 by C del lambda del T, and there's a del T of. So what I'm going to do over here is I'm going to call this E. Okay. Now, given uh, given this response, okay, you can immediately generalize. So given this response of this grad lambda and 1 by C del lambda delta T, you can basically find out what is the response of A and phi, okay, by putting it over here, by putting in the above equation. So you'll find this gives my delta A. So write this down because these are all very important and you have to work through it. Delta A is equal to minus delta T del T of A plus phi C delta T, and your delta phi will be minus delta T del T of phi minus phi del T of. Okay. So I'm going to call this B. This again can be written in terms of, again using this equation and the equation for over here. Where is it? Equation for E and B basically. You can write this equation, recast this equation. So this can be recast. It's not very difficult. Recast as. So I'll go through this algebra because at the end of it brings something very interesting. We'll see, you'll get a C delta T times E plus tens of phi C delta T, and over here delta phi will give you 0. I'm putting in a 0 by hand. It will become clear why I'm putting this 0 over here. Minus 1 by C del T of phi C delta T. Okay. So let me write this as. Now you look at these equations. Okay. So go back over here. We have these gauge transforms, and we know if we have a gauge transform where A and phi they change in this particular way, then they do not affect E and B. So they do not affect the fields. Okay. Now look over here. How does the change in the small response of A and phi has come out to be? The small response of A and phi, if you look at, this is coming out as having two gauge transforms. Okay. So think of this, the response has two gauge transforms, okay, given transforms. Hello?
Once
Oh, something is happening over here. What the hell is this? Okay. Two gauge transforms given by the scalar phi c delta t. Okay. So they will not contribute. They will not contribute to changes in the field strength. So anything which is like this in A and phi are like gauge transformed by this quantity, and so they will not contribute the changes in this field strength. So the changes in the field strength will effectively come due to changes in del A and phi. So the changes in the field strength, changes in the field strength will effectively come from delta A is equal to this thing, this part, the first part, Ct C delta T times E, and delta phi is equal to 0. This is why I had a 0 over here, because the second part will not give any change in the field strength. Just give me a second. Right. So now you use the connection between E and B and A and phi and write down what will be the corresponding delta E and delta B corresponding to this delta A and delta phi. But delta A is only C delta T times E and delta phi is 0. Okay. So if you do that, then we will have, so again, do the calculation. We'll have a delta E, okay. This will be minus 1 by C del T of C delta T times E. Okay. And this you can further simplify by delta T del T of E del T of delta T. And similarly, we'll have a delta B, which is equal to curl of C delta T times E. This you can use basically curl of E is equal to minus 1 by C del B del T. So use that. And this you will see minus delta T into del T of B minus E cross this is what you'll get. So over here, I have used the equation, as I said, that curl of E is minus 1 by C del B del T. So you have variations of the response of the electric field and response of the magnetic field to the small time change. Okay. Now, what I want to do is go back to the Lagrangian. So this is quite time far back, so I don't want to scroll back. So go back to the total Lagrangian. So now go back to the total Lagrangian. Go back to the total Lagrangian that we had. Remember, it had a particle part and a field part. Now in the field part, if you use the fact that B is curl of A and then E has this, so if you use those conditions, then some part of the field part goes away. Okay, so we can write down the homogeneous, okay, field equations. So by using fields in terms of potentials. So use the fields in terms of potentials, then in the field part of the Lagrangian, you can go back and check. The first two terms will cancel out. Okay. Well, not cancel out completely. It will leave some terms which will then add it to the third term. You will see that the field Lagrangian, the Lagrangian field will basically just become 1 by 8 pi b squared minus b squared. Okay. This is what we'll do. The other parts will cancel out. So it's very easy to check. Okay, so this is what we get. So we can work with this now. So we have, because we are using gauge transformation, and in gauge transformation, of course, we are using it because that also connects your E and B to A and phi. So we've used E and B in terms of A and phi to eliminate this A and phi, and basically the field part remains E squared minus B squared by 8 pi. So now that this is like this, if you know the field, now I can do the variation of this field. So now I have got the response of E and B as a response to the small infinitesimal time translation. So I can find the response of the Lagrangian to the whole thing. Okay. So now I can find, okay, we can find the response of the L field due to delta t or t. So L field, remember, is function of E, B, and T. Okay, there is also a T over there. So basically now write down what is L field, what is delta L field in terms of delta E, delta B, delta T, all these things. So just write it down. Okay. So when you do that, so use some algebra, 2-3 lines of algebra, you will find that your delta L field, the response of the Lagrangian of the field part, will be minus delta t, del t of L field, of course, the first thing, and then the E and B terms, which you can write down as minus 1 by 4 pi b squared del t of delta t minus C by 4 pi E plus B dot. Now all these things may look gibberish. It will only make sense when you basically work out the steps. Okay, so this is very important that you work out the steps. I'm not going to work out all the steps over here. So this can be simplified. So I'm going to give you the last step. This can be simplified as minus del t of delta t times L field, okay, minus 1 by 8 pi b squared plus b squared, then del t of delta t minus C by 4 pi E cross B dot. Okay. So this is finally what we'll find for the response of the field part of the Lagrangian. So let me again call this E. Now, before we proceed further, what we want to do is do exactly what you have done, the technique which you have done before when you did the Lagrangians, is you go back to the particle part of the Lagrangian and write it like a field. So write down the particle part as a field. So now let us write down the L particle like a field. Okay. So what we have is basically we'll have to, instead of charges, so we have to put in charge densities and velocities. Okay, so that will become current densities. So we are going to integrate over the volume by putting in delta functions. So what will happen is now my L particle will be an integral of some Lagrangian density of the particle, where this is basically sum over I of the solution, I Lagrangian densities of the particles. Okay. So now let me write down. So you have to go back to the Lagrangian and see how that whole Lagrangian was. So you have to scroll back through classes, and we'll see that I can write down my this Lagrangian density of the particle by Li. I can write down in terms of the delta function. So delta R minus Ri, which is function of t. And then we have half mi pi squared. So qi phi t, okay, plus qi by c pi at t dot. So when I did this, I did one more thing. Remember, there was a momentum term in the total Lagrangian. I went into the Lagrangian viewpoint. So we wrote down the total Lagrangian. When I wrote down the total Lagrangian over there, remember there was a first term in the particle which had momentum, pi also over there, because that was the mixed viewpoint. When you want to go back to the Lagrangian viewpoint, you basically make into account, use, so we have used bi is equal to dri dt to go to the Lagrangian viewpoint. So the first term basically got was away. Okay. So this is what we get. Now we have to go more. We have to find the response of this. Okay. So we have to find the effect of the small time displacement on R. So what we need to find over here. So we need to find, okay, we need to find the effect of delta t, okay, on basically my on R. This is what we want to find. So use the same way how we calculate the response. Okay. So to do that, we have the same way as we calculate the response. We have Ri plus delta Ri, okay, at t plus delta t is equal to Ri. And so this will give you delta Ri at t is equal to minus delta t, which will depend on Ri at t in full generality, and then dri dt, which is basically the velocity. So vi, this is what we'll get. So this is the response on Ri. Similarly, you have to find the velocity variation. So you have to go one step, every step like this. Okay. So this is position variation. Then we have velocity variation. If you do the velocity variation, so basically what I want is delta vi, the function of t. This is quite easy. Okay. So minus delta t, Ri t, t of vi of t minus, so we are doing on both of them, both on the terms on the top, okay, minus vi of t, and then the ddt I'm going to divide into del del t and v dot grad, because I can always do that. Okay, so over here I'm going to do del del t of delta t plus vi dot grad of delta t. So this term was actually ddt, which I basically the whole thing I divided into implicit, explicit, this kind of stuff. So I've used this. So this is where we have found how my variation in the velocity. Now that is not all. Now we have to go and see how this changes. Okay. So we have changed, we have seen the variation in the position, we have seen the variation of velocity. Now we have to find what is the variation in the potential. So this is phi I and AI, okay, meaning phi at Ri and A at Ri, okay. So how those things change, okay. So now find the variation in the potentials. So variation in the potentials in the Lagrangian part, the particle part of the Lagrangian, that we need. Okay. So I'm not going to work it out. I'm going to give you the final result of that. Again, this is not too much of working. This is 1-2 steps every time, but you must do this 1-2 steps. I'm telling you again and again, please do those 1 and 2 steps and go through the results. So what I'm going to do over here, if you go back to the Lagrangian, if you look at the Lagrangian and see how it changes due to the changes over here and here, then you will find that my delta phi, okay, at Ri, which is a function of t, so this thing will be minus delta t, del del t of phi, minus phi del del t of delta t, minus delta t times vi dot grad phi. Okay. And this you can write down as, let me find out where I wrote it. This becomes very simple. So this becomes delta t minus delta t of phi minus similarly we find that this thing can be written as finally as minus delta t ddt t of A plus phi C.
So in the delta phi equation, you left the third term when you are writing it again.
Delta phi equation.
In the second equal to sign, you left the third term, which was there in the previous line, but it's not there in the next line. The delta t pi dot grad
No,
I.
see, there's a small difference. One was a
Oh,
del.
okay. Sorry.
See, there's a del.
Yeah. Sorry.
Yes. Okay. So I'm always playing with sometimes with del and sometimes with dd. Okay. And something. Okay, I'll say this in a moment, and it will be clear when I want to del when I want. Okay. Now, if we add all this, okay, then the total variations we're adding up. Add. We have total variation of particle. Okay, so total variation of this particle. This will come out to be delta Li, which is equal to minus d dt of delta t Li minus, boards are so small I can't fish, so minus delta function of r minus ri, okay, at a t. I try to be as specific as possible. Then I'm going to write down ki. I'll tell you what ki is. Okay. Then I will have a del t of delta t plus vi dot delta t. Over here, my ki, where my ki is basically half mi vi squared. So it's the kinetic energy. Okay. Now, one thing you should notice, and this is what exactly what was the confusion before, is that now, okay, since we're back in the field space, so we have written all the particles also in terms of the field, okay, at a particular position in R space, what we can do is that we can write everything in terms of del t. So everything which was d dt now over here, I can actually write it in terms of del t if I fix my R. So in field space at a particular position of R, I can go to this variable where I write everything in terms of del t, referring to all t dependencies. So what I want to say is that, so everything now is in field space in a sense, right? So I've written the particle part also in terms of field. Then for a particular R, we can write the t dependence explicitly, okay? So referring to also, and so basically have only del t. So the first term had a ddt of delta t li, this one. Okay, I can even get that if I fix my r to make it del t. Okay. So then what we will have is I will have this will be in terms of del t. So everything over here is in terms of del t. So then I can add my field. So this field definition of this particle space with the previous, where is it? Over here, this L field, which was the actual field variation that we had before. So you can add E with, let's say, let me call this F. Okay. And now add E and F. Okay. So if we add E and F, we'll get again a very big equation. Okay. I'm not going to write down this very big equation. So although I have written it down in my notes, I'm not going to write it down. It just takes too much of time. But I'll show it how it's done. Okay. So give it, just I'll basically skip a couple of steps. Okay. So what I can do is that if I add my E and F, so look at your notes very carefully. This is the F part and the E part was before, which was the field part. We add the both parts. We will find that my delta L total, which was basically delta L field plus delta L particle. This we'll find is given by, so my delta L total is given by del T of delta T L total. Okay, so now it's no more just field or particle, it's L total now because we added both the things, minus what I will say U total into del T of delta T minus, again, so I'm going to define this S total dot. So this is a very interesting equation. Let me try to go over it. So what we'll find is you can write the total variation due to the small infinitesimal time translation. The total response of the Lagrangian is this. So I've basically subsumed everything in this U total and S total, where this U total turns out to be 1 by 8 pi E squared plus B squared plus summation over I delta R minus Ri T times Ki. Okay. And your S total, okay, so your S total basically is C by 4 pi E cross B plus again another summation of delta R minus Ri T, and then over here is Ki times Pi. Okay. So this, of course, you recognize. So this is your total energy density. Total energy density. And this one is basically your total energy flux vector. Okay. So your Lagrangian variation has the total energy density and the total energy flux vector in it. Okay. So now if your Lagrangian is varied, you can find out what has happened to the action. Okay. Now remember, what we're trying to do is we're trying to look at very local variations. So we want to find the local variation of action. We are not very keen when you look at this variation at the endpoints. Okay. So what we can do basically is that we can ignore these boundary conditions, okay, of the stationary action principle, and set this delta RT at these two endpoints to be 0. So we ignore, so delta L will give you a delta S action, okay? But we can ignore the boundary effects over here because we are looking at infinitesimal small local variations, okay? In the stationary action principle and set my delta T, R, and T, okay, equal to 0 at both T1 and T2. So over there, we do not have any changes, the same. Okay. Only there's a small infinite changes somewhere in the middle. So you do that, if you do that, then what we have a delta S, okay. This will be from T1 to T2, dt, and then the integral of the Lagrangian, which is the integral of the Lagrangian density. So d cube R delta T del T of U dot plus and this of course is equal to 0. And this now obviously means that if this has to be 0 at any position in between the two time extremes and at any position in R, then this basically means that my del T of U dot plus divergence of x dot is equal to 0. And when I say dot over here, this is dot in the sense of this dot, so field plus charges, not in the sense of the total volume. Okay. So this is basically a local statement of energy conservation. So a local energy conservation. Okay. So what we have found is that if I have just like a global translation in time, gave you a global energy conservation law, the same thing sort of happens very small at locally infinitesimal volume. So if a small region of the total volume also has a small time translation, then the response over there also leads to a local energy conservation law. Okay. Now, one thing you should realize over here is that what you have done before, if you have done ED1, then you would have done basically energy conservation laws, which was something like this. So in ED1, so this thing is basically, as you can see, this this sort of generalizes ED1 conservation law, which was basically del T of E squared plus B squared over 8 pi plus divergence of C by 4 pi E cross B. Okay, it's equal to 0, where this thing you knew as the Poynting vector. Okay. This was when there is no charges. In the absence of charges, this was the conservation. This has been generalized where both this S and U now has charges involved in it. So see over here, It is not only the Poynting vector, this S over also has the flux from the charges, the U also has the energy from the charges. This is a generalization of the simple energy conservation, local energy conservation law that you had in your ED1. This comes from your proper gauge transformation of the total Lagrangian. Okay. Okay, so thing I want you to do is this. This was F. This is G. So your homework turns out to be this. Homework. Calculate all the steps leading from equations A to equation H. So everywhere that I've gone through, even that took me an hour almost. There have been steps that I have not said. Okay. So your homework is you should calculate, fill up all the steps that are, so everywhere there's a 2-3 steps in between. You fill up all the steps, show it in detail that you actually get whatever I have seen over here. There is one more homework that I want to give. This is slightly more complicated, and I hope you guys will attempt it. So for that homework to do, you must do this homework first, so that you're confident that you can work through the steps. Okay. The second homework that I want to give you is this. So over here, just analogous to delta t, okay, which is a function of r and t, have a delta r, okay, which is a function of r and t. So it's no more time translation, so it's local space translation. Then work out the equivalent equations A to H. Okay. Show that this gives the conservation relation between the field momentum density and the stress dyadic. Okay. So find out what is the field momentum density, find out the stress dyadic, and you are probably going to do it again. Write it down. So show that instead of delta t translation, if you have a delta r translation, then you will get this conservation law, local momentum relation between field momentum density and the stress dyadic. Okay. This is it. Now, after this, we sort of come to the end of a lot of things. What I was thinking was I would do a little more and talk to you about how these conservation laws relate to the speed of light. Okay. So let's see how much time I have. I have around 20 minutes. If I rush through it, I think I can do it. But and that will naturally actually relate conservation laws, your Lagrangians, all these things that you have done and relate to speed of light, which will relate to your special theory. You'll see that a lot of the structure of the special theory was already built in this, the way we have written. Of course, we said this before, but we'll see it once again. Okay. So should I start? Hmm? Let me go ahead and do a little bit of this. Okay. So this is actually a fun part, and it's not, this part will not have too much of detailed calculations like before. It's quite fun. So let us do it quickly. So you want to talk about you want to connect conservation laws to speed of light. Okay. This is our motivation. Okay. So over here, what we're going to do is we are going to talk about electromagnetic fields in the absence of charged particles. So far away from charged particles, okay? Because we want to speed of light, so we want to something to propagate. So we want far away from charged particles. And in finite region of electromagnetic fields, okay? So basically we'll talk about regions which are pulses. So think of an electromagnetic pulse, it is moving. So electromagnetic pulse is a finite region in space. It has some electromagnetic field, and this electromagnetic field is propagating. Okay. So we want to look at, okay, so EM fields. Look at EM fields, okay, free of charges, okay, moving, having finite volume. So basically pulses, okay, pulses of, okay, this is what I'm going to do. Now within the pulses there is energy conservation. Okay, so there is some energy and it is taking away the energy. There is no dissipation. So the total EM energy of such a pulse is constant in time. The total EM energy of the pulse is constant in time. Okay. So basically, if I think of ddt of the energy, so over here is the energy, okay, that is 0, so is constant. Okay, so this basically tells me that if I look at my pulse and look at the energy conservation law that we have done before or now, okay, get rid of the charges part, so only have the field part. It will basically the energy conservation that we did before actually. Okay, then over here in that pulse volume, I have a del T of U, and this is minus again pulse okay. So over here the surface integral is such that is enclosed over conducting surface, which is very far away, big enough that all the fields vanish. So that's how we get it. Okay. So surface integral is 0. Okay. Goes far away, fields, touch. So this is the energy thing of the pulse. Similarly, you can write for momentum and also for angular momentum. Both you can write. I'm not going to work out momentum and angular momentum because this is all you're supposed to know in your ET1. So I'm not going to do that, but I'm just going to write down the equation. Okay. So similarly, so this is for energy. Similarly for momentum and angular momentum. So similarly, we have for momentum and angular momentum. Okay. So for momentum, we have dt of momentum. So P, the linear momentum, that is equal to 0. Okay. So you think that momentum is also conserved in the pulse. And so again, I can write it down in terms of this 2 integral, where the surface integral will give you a 0. Okay. So this is pulse dqr, okay, del t of g. G is the momentum density. Okay. This is equal to minus, again, pulse, and then this is again dqr. T is equal to 0. But T is basically the stress dyadic. Okay. So G over here is equal to E cross B over 4 pi C. This is the momentum density. And T, which is the stress dyadic, this is, to explain this in a moment. Okay. E squared plus E squared by 8 pi minus, there's a direct product of electric field and magnetic field, right? 4 pi. This one is a matrix, okay? So it's a unit matrix where my one, this matrix is basically delta KL. This is a Kronecker delta. So only the diagonal elements are 1, the off diagonal elements are 0. Okay. And has 3, because there's 3 spatial directions, so there's 3. K goes on 1, 2, 3, L goes on 1, 2, 3. Okay. So that's how I define my momentum density and the stress dyadic. So this is for the linear momentum. I can write it down also for the angular momentum. Again, these are the things that you should have done before. Okay. This is conserved, I would say, within the pulse. And since this is conserved, again, I can do basically for the pulse, I will have a dqr, okay. And since it's the angular momentum, it is basically r cross g. So this is r cross g. This becomes minus of, okay, pulse dqr. And again, there's an r cross over here. So this over here, this t cross r, it becomes. So divergence minus t cross r. Instead of r cross t, I have put it as minus t cross r. So this is the angular momentum, where this part is the angular momentum density, this part is the equivalent angular momentum stress. Now we have an equation for energy, we have an equation for momentum. Both has a 0 over here. So in principle, we can add them. Okay, 0 plus 0 is 0. So with an eye towards relativity, we can add this space, this energy, and the linear momentum. Okay, so energy, so the space component, and the momentum, which is the time, energy, which is the time component, and the momentum, which is the space component, add them together. So we can add, we can add, the space and time components. And if I do that, then what I have, so I'll write it in terms of this dyadic. So I write it in terms of xi, xj, xk. Okay, in that sense, I'll write it down. So in that sense, in the matrix form, what you will find that you will have your xk into del t of u plus z, okay, minus this c squared will appear because there's a c in both, okay, on top and bottom. So we can have a c squared because this top and bottom c will multiply to get a c squared, okay, t, then you have a del t of k plus dlk, and this is going to be equal to 0. Okay. So I have added the first part, which is the time component, the energy component, and then I have added it with the space component. So this, remember, is outside the charge distribution. So this is in the wave pulse. Okay. So this is outside the charge distribution. So remember this. Okay. Now, if you go back and do an ED1, there is a connection between this Poynting vector S and the momentum density G. You'll find that your S is basically your C squared G. Okay. This used to be a problem. I think last time I gave a problem on this. Okay. So I can use this part. Okay. I can write down this local conservation law. So I'll use this. So use this, and then I can write down my local conservation law like this. So I will use this, and I will have del t. By the way, one thing I wanted to say is that over here, if you look at this momentum density c squared g, on one side, so in one side, you have mass density times velocity, okay? And on the other side, you have basically energy density times velocity. Okay. So let me actually have this, make this comment. It's very interesting comment. Got this. So this equation has energy density times velocity as c squared into mass density times velocity. Okay. So this is actually a first indication of E equal to mc squared, which is already being there in the way that EM theory has developed. So in EM theory, the fact that it will be compatible with relativity that will come in the future is already there. See, over here you will have your E as mc squared. Okay. So you can look at this. Anyway, we'll use this term over here to simplify the above equation. So when we do that, this is what we get. Okay. To simplify, so we'll have a There is a square G. Squared this I've used. So I've used this connection between the momentum density and the Poynting vector to rewrite this equation. When I'm going to integrate this again over a pulse, then the second term, the surface term, does not contribute. So if I integrate, over the local pulse volume, the surface term do not contribute. Okay. So then the second term is 0, and I'm integrating with the local pulse volume. So what I get is I will have a d dt. Okay. So this is local, so my R is now fixed. So my del t becomes d dt. Okay. So d dt over the pulse TQR is local pulse volume. And so this becomes RU minus C squared TG. This is equal to 0. Now the volume integral of the momentum density. So now I can integrate it by side, the two terms in it. The volume integral of the momentum density is the momentum, right? So now if I integrate this thing, GQRG, this is the momentum, okay? And so this is constant in time that we have found, that we know, because momentum is not changing. So this is constant in time. So then what I can do, I can rewrite this previous equation because this is constant in time. Therefore, I can rewrite this previous equation, and this will become d dt again over the pulse, integrate over the pulse. Okay, I try to write it every time so that it is clear into the volume of the pulse. Okay, this RU is equal to C squared. So now, if I look at the left-hand side of this equation, what I'm doing over here is I'm integrating this energy, I'm weighting by the position vector. So this thing is basically, I'm integrating the energy by weighting it by the position vector, right? So I have an R over here. So I'm integrating the energy, weighting it by the position vector. Okay. So this I can basically think of it like this. So it is, so this thing is basically, if I d cube R, okay, times R U, which again is a function, remember, of R and T. This is my energy. Okay. I have some position vector weighting. Okay. and my energy E is basically now look at all these equations one after the other. Okay, so if I combine this last two equations with the previous equation of this momentum being P, then you'll see that the motion of this pulse, okay, this energy centroid, because the energy is weighted by some position. So motion of this positional variation of the energy, okay, is governed by this equation, okay, which now I have rewritten in terms of this equation and this equation. So therefore, what I can say is if I combine these three equations that I've marked, we'll see that the motion of the energy pulse, okay, this you will see is given by E by c squared d dt of some r, okay, function of t. This thing is also a function of t. This is equal to, which basically tells me, so now it has two portions. Here is a portion and here is a portion, okay. This portion tells me that it is moving with some constant velocity. So this tells me it is moving with a constant velocity, okay. I will call that, let's say, VE. So the energy is traveling with a constant velocity, that's why it's moving VE, okay. Where the momentum, okay, is given by this velocity multiplied by a mass, where this is like the mass, okay. So m is equal to E by c squared. Okay. So from this equation, what I'm saying is that this energy in the pulse is moving with some constant velocity, which is v, where the momentum of that thing is governed by a mass, where the mass is connected to the total energy of that pulse by c squared. Now we're going to do a little bit more to connect this velocity v with the velocity of light, slightly more. So this remember this time that we have now actually got a velocity, defined some velocity of the system, which is a constant velocity at which the energy is moving, which is the VE. Okay, if the mass is given by E by c squared. Now this packet pulse also, as you said, the momentum is conserved. The momentum is also being carried away by this pulse. Okay. So what I want to do right now is to see at what speed the momentum is moving. To do that, we have to write down an equation, and I'm not going to write down the equation, not going to derive the equation. So I'm going to use the virial theorem. Okay. So I'm going to use, so maybe I can give you it as a homework, but it doesn't matter. You can look it up, how to get the virial theorem for electromagnetic ED. So virial theorem in ED, okay. The full virial theorem in ED basically tells you, this is the virial theorem, del del T of R dot G, okay, plus divergence of T dot R minus U plus R dot F. Is equal to 0. This F is nothing but the if the force is the big F, then this is basically the integral of. So this is a force density. So this is the equation for the virial theorem in ED. I have not derived this equation, but just trust me, this is the equation for the virial theorem. Now over here, if I fix my R, so at the position of the pulse, okay, what I'll find that this will reduce to a smaller equation, okay. So first, we infer that this pulse also has a velocity. So if I write down like this, let me write down this d dt. So again, remember del del t becomes d dt because we are fixing an R. Okay. D dt of the pulse. Okay. This is dq R. R dot g. This is equal to E. This E is nothing but dqr. So this is what we get because the other parts become 0 when I fix my R. Okay. Now, what I want to do is that I'm going to do a momentum weighting. Just like previously we had and position weighting of the energy, I'm going to find a momentum weighting by the position vector. So we want to weigh the momentum by the position vector. Okay. How do you do it? Very simple. This is dqr. You have the R times G. Okay. This is now weighted by the position vector, so you can have R. Okay. This is momentum P, which is a function of T dot and so from here, okay, you'll see that the centroid of this momentum weighted pulse, so rather the centroid of this momentum, which is associated with the pulse, this momentum is also having some velocity, okay. So the center of momentum, this tells you the center of momentum also travels with the velocity. And let me call for the sake that this velocity is at present, I want to distinguish between the previous velocity, which was how the energy was moving. I will call it as Vp. Okay. So this d dt, okay, of this R and this is constant. So if you manipulate the previous equation, manipulate this previous equation, okay, this equation that you have over here in the black, then you will find we get from here, okay, we get from using this equation and this, basically with these three equations, we get Vp dot P, this is equal to so we have got this equation over here, and we have got the previous equation. Where is it? We got one more equation over here. Okay. If we now use these two equations together, then what we have, so let me say equation, let me call this equation, I don't know, equation equation 1. Equation 1, I'll call this equation 2, combining equation 1 and 2. What we'll have is we will have Vp dot Ve is equal to c squared. This is what we get. Now, of course, we have one more leap of faith. So if there is a pulse in which the energy is traveling at a speed which we call V, and the same pulse in which the momentum is also traveling at a speed which we call Vp, then it makes sense to think that both Vp and Ve are the same because they're both traveling with the pulse, right? So if I make that with a single velocity, so now because both Vp and V traveling with the pulse, they can be taken to be the single velocity v. Okay. So what we have now then, v dot v is equal to c squared, which basically tells me that my v is equal to c. So this sort of identifies the speed at which an electromagnetic field in a pulse, electromagnetic radiation is moving, the velocity at which it is moving is actually the speed of light. Okay, so this is a physical identification of the speed of propagation of the pulse to be the speed of light. Of course, when we did Maxwell's equation in our first two classes, we had assumed this, right? So this was built into our assumption that, well, the third assumption was that things move with the speed of light. But over here, we have got back that actually the pulse is moving with the speed of light. So there is an internal consistency between Maxwell's equation and that the pulses are moving with the speed of light. Okay. So that's a nice thing. It's a very interesting that comes out because of this conservation laws, that because of the conservation laws, when we applied to a pulse away from the charges, if the energy is carried by the pulse and the momentum is carried by the pulse, then the energy and momentum should both move with the velocity, which will be the speed of light. One more thing we can do, I don't have time right now, but it's a very interesting thing. So I will just add it in the notes. You could show that this conservation law also tells you one more very interesting thing. So not only it moves with the speed of light, but the electromagnetic fields in the pulse should be perpendicular to each other and perpendicular to the direction. That also can be beautifully shown from this manipulating this conservation laws. I will add that to this note, okay, and post it together. So that, I guess these are things that you have not done in this way before. This is a new way of looking at most of this stuff, and I hope you find these things interesting, because ED is something that you have been doing for many years now. It's difficult to make ED any more interesting by, so I've tried to do things a little differently. Okay, so that's it. I'm also host talking for such a long time, and also I have, I don't write so much these days, so my hand pains when I start writing for such a long time. So we'll stop over here, and on Friday we'll get back. Remember 4:15. We'll start with something new. We'll start with special theory. So initial class will be very simple. We'll just quickly go through postulates and things that we know for special theory, and then again we try to do it a little differently than what we have done before. So that's it. For all of you guys, Happy New Year. I'm sure someone has Happy New Year today, tomorrow, or day before yesterday. So in 3 days, we're just in the middle. Happy New Year. So enjoy. Okay. Is there any questions? Otherwise, you can just stop the recording. Nothing? Okay, then. Okay, one can stop the recording then, and we'll leave for today.